Let's now understand how nested function calls work in assembly. Here we have our high-level language code with three functions. The main function calls add function with two parameters. The add function calls add num function with the same two parameters. The add num function does the addition and returns the result to add function. Now this function simply returns the same result back to main function. In assembly, we have three labels, each corresponding to one of the functions in the high-level language code. Let's start writing with the main function. The main function simply moves value 5 to R0, which corresponds to X, value 10 to R1, which corresponds to Y, and then it makes a function call to the add function. Add function here just makes a function call to add num function, so we use BL, which calls add num function, and then it returns back to the main function. Add num function does the addition and returns back to add function. So this is how assembly code for nested function calls can be written. Now let's try to see what happens when we try to execute this code. When we execute BL, the R14 register is updated to point to the instruction immediately following it, so that when we come back from the function call, this is the instruction that should be executed. Then this BL instruction will again change R14 to the instruction immediately following it, which is this instruction. Then after doing the addition, we execute move instruction to return back to the add function. And what it does is it takes the value of R14 and puts it into the PC register. So R14 is pointing to move instruction. So the PC will now point to this instruction, and the next instruction that will be executed is this instruction. So by executing this move instruction, we have successfully come back from add num function to add function. Now what we expect to happen next is that add function would return to the main function. So let's see what happens when we try to execute this move instruction. So it takes the value of R14 and loads it into register R15. So where is R14 pointing now? It's still pointing to this move instruction. So PC will again be set to this instruction, and the next instruction that executes will still be this instruction. So as the effect of executing this instruction, the PC will always keep pointing to the same instruction, which means we are in an infinite loop. So how did this happen? Where did we go wrong that caused us to stuck in an infinite loop? Just think about it a moment. Where did we make a mistake? Okay, when we executed this BL instruction, it overwrote the value of R14 without saving it. So this BL instruction wrote R14 so that it points to instruction immediately following it, somewhere here. However, when we executed this one, it simply overwrote whatever was there in R14. As a result, we lost the link which was linking this move instruction to instruction immediately after this BL instruction. And as we lost that link, we are stuck in an infinite loop. So what we can do to solve this problem? As you can imagine, the solution is not to overwrite it blindly. Rather, first save what was there in R14 and then write to it. So what do? We save the return address from R14 to stack before writing to the R14. So what's this stack? Stack is a piece of memory which operates as last in first out manner. So whatever is the latest thing that gets into the memory, that is the first one to come out. The last occupied position in stack is always pointed to by stack pointer or the register R13. Historically, stack grows downwards, which means if you add something to the stack pointer decreases, and if you take out something from the stack pointer increases. There are also special instructions to access the stack. Push instruction stores data to stack. For example, this push R4, R5 will take the contents of R4 register and R5 register and save them into the stack. Similarly, the pop instruction will take the content of the memory location where stack pointer is pointing and save them into register R2. Now, as a side effect of executing push and pop instruction, the stack pointer automatically moves up or down. We do not need to do that manually. The implementation of push and pop itself handles that. Let's take an example of how stack really works. So here is our memory. Some of the locations are already filled. Stack pointer is pointing to the last occupied location. Now let's see what happens when we do push and pop. First, we want to execute instruction push R1. What will happen is it will automatically reduce the stack pointer to make space for the new value that we want to write, and then this value will be written into the stack. If you see, after executing this instruction, the stack pointer is still pointing to the last occupied location in the stack. Same, we do push R2. We will first make space in the stack by reducing the stack pointer, and then write the value of the register R2 into the stack. Pop R2 does the opposite. It will read the memory location to which SP is pointing, take that value and store it in register R2 and increase the stack pointer. So that now this is the last occupied location. This location is actually free now. Pop R1, it will again do the similar thing. It will take the value from the memory location to which SP is pointing and save that value to register R1 and increase the stack pointer to point to the next location. Now this is the last occupied location. These locations are now available for writing something else. So if you see, the order in which we push registers to stack is the reverse of the order in which we pop the registers. This is to ensure that the contents of the registers stay same as they were before doing this push and pop. So since last in is R2, first out is also R2, so that the content of R2 stay the same. Okay, since stack is just a piece of memory, we can use regular load store instructions to update it. However, we need to update the stack pointer manually in that case. Let's take an example. So we want to again do the same thing, put the values of R1 and R2 into the stack, but instead of using push instruction and pop instructions, we will use regular load store instructions. So first thing we need to do is make space in the stack to store these values. For that, we will reduce the value of R13, the stack pointer, by 8 so that we make space for two 32-bit numbers there. So now we have these two locations available to us. Then we do a store instruction. We are writing the content of R1 to a location where base address is R13. So R13 is this is where stack pointer is pointing, plus 4. So you go up plus 4. So here, this is where you want to write R1. So this is R1 is written. Next, we want to write R2 to a location where R13 is pointing. So R13 is pointing here, and you store the content of R2 there. Now, what we want to do is to pop the values from the stack. We don't really need to do that because R1 and R2 still have the same values that they had before. All we need to do is to move the stack pointer back to its original place, and that can be done using an add instruction. So we add 8 to R13 and stack pointers move back to its original position. Let's see two important things here. So in both cases, even though we moved the stack pointer down here and then moved back after putting the values of R1 and R2 in the memory, so when we pop these values using pop instructions, it's not that we are destroying these values from the memories. The values are still written there. It's just we should not touch this piece of memory now because they are out of our stack. Our stack is only from this location upwards. Maybe the values are still there, but it's not really our space now. We have already given up this space. Also, when you push the contents of R1 and R2 to the stack, it doesn't mean that R1 and R2's contents are destroyed now. It's just a copy of those content resides in the memory now. The value of R1 is still the same as it was before doing the push. Okay, now we know how the stack works. So let's use stack to correctly do the nested function calls. So this is a piece of code that we had before. This is the BL instruction, and there was a problem here in the add that this BL instruction overrode the contents of R14. So what we can do is, before doing this BL instruction, we save the content of the register R14. To do that, what we can do is, we just push the value of R14 to the stack. Now, when this instruction executes, we have already saved the value of R14 so that later when we need it, we can retrieve it. And how do we retrieve this value? By doing a pop instruction. So once we have executed this branch and link instruction, we are in this piece of code. This move instruction will now return the execution to this pop instruction. And now this pop instruction will go to the stack. Whatever is there at the stack top, wherever the SP is pointing, it will take that value and put that directly into R15, even though we pushed R14. The reason is because anyhow, after doing the pop, we were about to move that value to R14. So here we are saving one instruction. We are directly popping the value into the PC register so that the next instruction to be executed is the instruction after this BL. So question, we are writing push and pop only in the add function. Do we need to do that in addNum and main function as well? Let's first talk about addNum. Since we do not have any BL instruction, we are not destroying the content of R14, so we don't really need to push the content of R14 to stack. So we don't need push and pop in addNum function. Main is a little bit tricky. Main function, when you start your execution, a bunch of system functions execute before you really reach the main. So there is actually some function usually that calls the main function. So in the main function also, we should write, so it just says that we are loading the value of R14 that we saved directly to the PC register instead of first loading to link register and then moving it to the PC register. So let's again talk about the main function. So in the main function also, we usually should do push and pop if it's being executed under operating system control. But if you are manually writing assembly code and you make sure main is the first function that you want to execute, then you don't really need push and pop. Okay, let's see what are the other things that we can use the stack for. We already know that it can be used to save COLI saved register. We saw that there are some registers that if the called function wants to use, it should preserve their values before really overwriting them. So where to save the values of these registers? Stack can be used for that. Stack can also be used to pass parameter and return values because there are only limited number of registers. So we know if we have only 4 parameters, they can be passed through register R0 to R3. But if we want to pass more parameters, they should be passed through the stack. Also, the local variables we need in a function can also be saved in the stack. And this is the order in which these things go. So the first thing that resides in the stack on a function call is the parameters which are passed. Then the caller context. These are basically the caller and COLI saved registers. Then the return address that we want to return to, and then the local variables of a function.